already gave you. It's just for you to look at. After you finish, I would like to have it back. Oh, come. Did you think you got it? Yeah. Did you look at it? Yeah. Any question on it? No. Question for the homework.
Yeah, so do we just assume a surface tension?
Do you need surface tension? What did they do? Did they use water and air? Use surface tension of air if you need surface tension. But I don't think you need any of that. Okay. Today we try to finish Taitel-Barnea model. Okay. Slab flow model. And then we move on to vertical flow. You done with that? In Taitel-Barnea model, I look up on the original publication, I see this equation. And I wonder if it is going to be the same as the equation that we have in the book. Okay? So I will try to start from the equation in the book and try to get that. Okay? So last time we talked about this equation, delta P sub U, right? And we have the, I said it's similar to 3.149, 3.147. Did you check those two equations? 3.147, 3.149? Is it the same? Okay, maybe it's a little bit difficult to see if it's the same or not if I don't show the equation. Well, 3.147, I have slab flow part and delta P mix, right? You see that delta P mix? And 149, I have definition of delta P mix. Combine them together, we should have this one. Okay? Should we? We have cosine theta term, right? And so instead of minus delta P mix, I substitute the minus delta P mix over there, and I have every term. Okay. I have cosine theta inside. Okay, instead of hs minus yb, I have this term and dh. The rest is kind of the same. But this equation, we already proved it, right? This equation is from previous lecture. Okay, this is 3.147. We have that, substitute everything. Okay, we start from the case where we neglect friction in the film zone. Right? So I get this equation, but not the one in the book. Right? Now let's start from here and try to get what is in the book. So this equation, let me remind you again, we derive from the case where we neglect that tau G, tau I, and pressure drop, frictional pressure loss in the film zone. So that's why we have LS, Okay, and this term is the acceleration term, or that is double Hubbard. For Taitel-Barnea, we have ls, and these two, that is for acceleration or pressure loss. Pressure loss due to acceleration plus pressure gain due to lifting it up. Okay, you still remember that? And we prove it from previous lecture. So now we want to see if this is in fact the same as the original one or not. Okay, the original one from Taitel-Barnea is that equation. Okay, last time we go through a little bit, and time is up, so we stop. Okay, now let's finish it up. So from this equation, this equation is derived from this one, right? Which is full form except nothing in the film. Okay, we have we neglect some part on the film. So let's go term by terms. The first term is rho g HLTB cosine theta. Okay, this term, when I split it into two parts, cut in half, I get this equation and that equation. Okay, the way I get that is, okay, cosine theta is not a function of height, right? It's kind of constant. I take it out. Okay, and integration of HLTB DHF. Okay, so that is like the area of rho g height, rho g dh. So that is hydrostatic head that we did earlier, which is this one. Okay, make sense? Where does that come from? Which equation in your book? You recall that? So that is like way before that we start. This is when we start double Hubbard or Taitel-Barnea. I believe it's 3.103, page 95. You see page 95? Okay. On page 95, we already proved that sometime that, okay, let's go here. We have this one, right? We went through that. We say, okay, d by dz of that part equal to that. Leibniz rule. Okay, you remember that? We use this one again. Okay, that's how I split it into two parts. Those two equations. Okay. The explanation is over here. The HRTBDH is 1 over AP and AF, DHF. Okay. And AF, I split into double integration. Last time we stopped somewhere around here. Double integration. I said, hey, let's not use AF, but we do integration from 0 to HF of B dy. How about that? This term will give me A sub F, right? Film area. Okay. Now let's take a look at the integration limit. HF and Z equal to LF, which is the top integration limit. That part, right? Is equal to HFE, or height at the equilibrium point. Okay. HF and Z equal to 0, or at the start, is HS. Liquid height at the starting point before we do the integration. Okay. And so we solve this equation. All right, from here, you may see something. instead of dy dHf, I swap it to be dHf and then dy. Does it make sense to you? How do we swap that? That is a little bit more on calculus part. So I look at the integration limit first. 0 to HF. Okay, and this is dy dHf. So I draw my axis. Hey, horizontal axis is y axis. Vertical axis is HF axis. Alright, now let's take a look. From 0 to HF, that HF is not a constant. But that HF is that variable, right? So this means the lower limit is what? Y equal to 0. The upper limit is y equal to HF. Y equal to 0 is, so y, right now y is horizontal axis. Y equal to 0 is vertical line, right? Y equal to 0 is vertical axis for this case. And y equal to HF is 45-degree line, right? And I do the integration from that line to that line. Okay? This is the integration, just the inner part. I don't care what's inside, I'm just looking at the integration limit. So when I draw it, I start from y equal to 0, which is that line, to y equal to HF, which is that line, so it's integrate this way. Alright? And then I do the integration. Outer limit is from HF equal to 0. HF equal to 0 is what? This line, right? That line, horizontal axis is HF equal to 0. HF equal to HFE, which is that line. So this means the integration domain is triangle. Okay. Step 1 we do from y equal to 0 to y equal to HF. So this means we move from left to right. And then we go from HF equal to 0, then HF equal to HFE. From left to right, and then we move up. Okay. Now I want to switch the integration limit. So that what I derive here is the same as what's in the book. Alright? So instead of move to the right and then up, now I want to do up and then right. It will be the same, right? Right and up and right should be the same. So up means from this line to that line. Okay. Now I don't want to use dy dHf. I want to use dHf dy. But the graph is the same. Okay. I want to do up. I have to start from that 45-degree line. And that 45-degree line is what? HF equal to y. So that's why my integration limit starts from there. Okay, so I start from the inclined line. And then I move until my HF equal to HFE, which is that line. So I move up, right? From 45-degree line to the horizontal line, but this time I write the equation in terms of y. HF equal to something, because I integrate with respect to dHf first. So I have to go up and right to be equivalent to go right and up. So when I move to the right, I move from that line until that line. So the first line here is y equal to 0, and this line is y equal to HFE. How do I know that? That line is y equal to HFE. How do you know that? Because the cross point. You see the cross point? I have to integrate until I get the same integration domain. That point is the point where HF equal to Y, and it happened that at that point HF is HFE, right? So this means that point Y also equal to HFE. So Y equal to HFE, this means vertical line. So that's why I go from Y equal to 0 to Y equal to HFE. Alright, that is swapping the integration limit. When you look at this, swapping the integration limit is nothing complicated if the limit, upper limit and lower limit are constant. If it is constant, you will get like rectangle shape and you just swap it, no problem. But whenever the integration limit is expression, variable, so this means we don't integrate. The integration domain is not rectangle, it's some kind of shape. So when we swap it, we have to maintain the shape. In this case, the shape is a triangle. Not only the shape, but direction too. Look at this. When we do the integration, we do from left to right and from bottom to top, right? When we swap it, we have to do bottom to top and left to right. We cannot do top to bottom and left to right. If you do that, you get opposite sign. Alright? Question? Question on this? No question? You understand completely? If you have question, ask me right now. No question? Okay, very good. So after we swap, then we do the integration inside. B DHF. Okay, B DHF. What is the relationship between B and DHF? You remember B is that line, right? This line. What about HF? The height. Then height at any location is whatever it is. So they are not a function of each other. B is a variable with respect to y. V is not SI tilde or SI anything. It has to change when y change, right? Y is this height. Okay? When we go up, B expand. So B is a function of y. It's not a constant. But it's irrelevant to the height. Okay? It's just a variable of y. So that is the reason that this part we can move B out. Okay? And we integrate inside. Integrate 1 is x from HF from HFE minus y. So that's why we get that. And B stay. Okay? So this part come from that. Oh, not come from, is one part of that, not the whole thing. So this is from 0 to HFE. It's the first term. That is the first term. Okay. Similarly, the second term will be that. Okay. So I have integration from 0 to FE of HRTBDF equal to that after we swap the integration limit. Okay. Therefore, equivalent to that equation, integration from, instead of from 0 to HFE, if we integrate from HS to HFE, we get what we already got minus the lower limit. Good? Okay. Substitute it in. Substitute this part in. Okay, into this equation. Then we have that equation. Alright, that equation, we have rho g sin theta, acceleration term but incomplete, right? Acceleration term of double Hubbard and tau in the slug body, chest rate in the slug body, and some pickup thing from that. Okay, is that the same as any equation that we have yet? I put it there 3.147 and 3.149. Is it? If you combine 3.147 and 3.149, is it the same? So you just substitute the delta P mix, right, to 3.147. I get the first term from 3.147. The second term, not yet. The third term comes from 3.47. And that term and the rest come from 3.149. Solve it? Did you see it? Yes. So this means what we derive when we neglect the tau in the film zone. It is actually the same as in the book, but we have to do some mathematical trick. Swap the limit of integration. And this kind of thing was explained like, what's that? 28 years ago? Is it 28 years ago? 1990 to 2000, 2010. 28 years ago. People know that. We should know that too. Alright? So this knowledge, is it anything relevant to what we are doing here? Not quite for the undergrad, no, but for graduate level. If you are about to develop your own model, make a new one, you got to know this. You got to know this trick, okay? So that we can follow the literature. Alright. So this means the full form for the equilibrium film thickness. We have this whole integration thing. We have proved that when we neglect the friction in the film zone, we can get the one, instead of the one with cosine theta, we can get the same thing that is in the book. Okay? What equation do we use? Do we use double Hubbard or Taitel-Barnea? At the end, so this is the proof that, okay, it's the same as the one in the literature or the one in the book. But at the end, what do we do? We can do several things. Okay? The full form is that. That is the full form. If we do some approximation, do a little approximation, you can see that, okay, the first term, we split it into, so that is rho u, which is slug unit. So we split it into gravitational term from the slug, gravitational term from the film. This split is with no assumption. Okay? The second one is Washer stress or friction term from the slug body. Of course, we keep it. Okay? The last one is where we have approximation here. Okay? So I say, hey, instead of doing integration, I use tau f sf over ap lf. So what this means is I take this whole thing out and I integrate 0 to lf. So I just first term multiplied by lf, second term multiplied by lf. I get that. Isaac, what is the assumption here? When we go from that equation to that equation, what is the assumption? Or we don't have any assumption. What is it? What did you say? Film something?
But the film math is all we don't neglect the film body.
We don't neglect what?
The film body. The length of the film.
The length of the film? What are you talking about? Victor, please.
Pressure drop in the film.
the height of the film is constant. Or that tau, look, SF, what is SF? Weighted parameter that curve from the bottom, right? How can it not be a function of Z? It is a function of Z because the height changed, so weighted part changed, right? Make sense? But here we say, hey, and that tau F changed or tau F doesn't change? It changed. Velocity changed. How do you calculate tau F? Velocity square, right?
You take the absolute, right? That's what
Kind of absolute, yes, but it depends on the magnitude, velocity square, but velocity keeps changing, right? So this means that tau F and that tau F is not the same thing.
So how many has
On the top is local at any Z. On the bottom is kind of average. Got it? Or equivalent to assume that the film is constant height. Alright? So that is first approximation. We can approximate more. Pressure drop in the gas pocket is small. Typically it's small. Okay? Most of the time, think about it. If you flow something fast, film is, okay, the length of film may be 2 times of the length of the slug body, but over there is slow. It's very slow. So friction is less. Hydrostatic head, not much. Okay, so we can neglect that and we have just this. Okay. The comment on here is, when you see, we don't have the acceleration of term. You see that? If we use acceleration term with the equilibrium film thickness, okay, and neglect the pressure drop in the film zone completely, it will be correct. The point that Taitel-Barnea says is, don't use that term. Okay. If we do it like Dr. Hubbard, it will over-predict pressure drop. Taitel-Barnea show the full form. If we want to do it completely correct, we do that. But if we want to do some quick approximation, like Dr. Hubbard, neglect that term. Got it? For equilibrium film thickness, neglect the film zone pressure drop completely. The accelerational term should not be included in the calculation. Should not. Do we trust them? Not yet. We have to see how do they validate that model. Now with the result, then we can trust them. Okay. We have model validation. This is the exact form. With exact form, this means we have to do like RK4 or some method to solve the film profile, do everything completely. So now let's take a look. Pressure drop, 0 degree, about 2 inch, okay. ULS or VSL is 1 meter per second. So full form, exact solution is a solid line, okay. So that is solid line. If we ever do equilibrium height, like Dr. Hubbard, so it's not going to match. Okay. So if we use acceleration term, it over-predict. You see that? This case is 0 degree. And we have 2 cases. So what this picture show you is like the diameter change, 0.5, okay, 0.05, 0.5. If it's small pipe, you don't even need a full form. It's almost the same. This is pressure drop per unit length. But we can do simplification like Dr. Hubbard. Just don't use acceleration term. That's it. It will be correct. But okay, not absolutely correct because this is a log scale. When it off a little bit, it can be quite a bit. Okay, now let's take a look at big pipe, 0.5. Okay, HF equal to HE, no acceleration term, is dot line, it's close. But if we put the acceleration term, it's far away. Right? So if we do Douglas-Hubbard model, of course, doesn't match. Neglect tau I and tau G, it doesn't match for low velocity, low SG. Full form will match. So when they show more cases and they like close to each other, then okay, now we can trust them.
But there is physical experiments there?
Where's the actual experiment? I don't think we have over here. I didn't show it in this slide. Maybe we have to go back to the original publication. Okay. All right. This 10% thing, I didn't put it on the blackboard yet. It will due like sometime in December. Haven't decided. But it is not due this month or next month. It will be in December. What I'm thinking about, okay, maybe grade submission day, or one day before grade submission day, or the exam day. Haven't finalized yet. Please go through this. This is optional. Several people last year did it. They get it right. But of course, it's a little bit difficult. Okay. What is this about? Okay. This additional homework is to repeat parts of Taitel-Barnea calculation. Expect about 4 to 8 hours of work for those who can do programming well, or 7 to 14 hours of work for those who have less programming experience. Okay. Calculate minus dpdz for cases where data equal to 0, d equal to 0.5, v equal to 1 meter per second, vsc equal to 1, 10, and 100. Okay. And use the same fluid property, everything the same as Taitel-Barnea. Use full form, use RK45. After you submit your homework, I'll give you my RK45. How about that? Okay. The first 50% of work due in neglect this first. Okay. Neglect this. Last time they do it like 2 parts, but I'm thinking about like, okay, I will put it on the blackboard. It will be in December. Neglect this then. Neglect this. Show the film profile of each case. Show results should be in the same order of magnitude of Taitel-Barnea. Submit source code, everything. This is individual work. So what I want is you repeat that line, right? But okay, you do 3 cases. VSG equal to 1, which is that point, 10, which is that point, and 100, which is that point. Okay? Just 3 points. Don't need to do it, and you actually cannot do it yet until you submit this homework and I give you RK45. Okay? Still sometime in December. Think about it, maybe do it during Thanksgiving. Okay? Okay, before we go to closure relationship and see the model performance, to make sure that you understand everything, let's check what we have last year for the quiz. Okay, this is a quiz solution. So the quiz solution, this is to chain integration limit. Okay? This is to check if you really understand the derivation that we have in class, that we have some integration trick. Okay? So 2 years ago, okay, I have this equation, 0 to 0.5, y to minus 1 of any function f, x, y, dx, dy. From the above integral, change the integration order to dy dx from the x dy. Do not change the function f inside the integral. Find proper integration limit for the integration in the form of something something dx dy. F xy is a certain real function which is defined, which is a function of x and y. How do we swap the integration limit? Okay. Step 1, draw a picture. Because the integration limit is not constant, and we have to draw a picture. But last year I draw a picture for students, so they don't have to do any picture thing. Okay, in this graph I plot x and y. Okay, I draw the picture. First is x equal to y, and then x equal to 1 minus y. X equal to y is that blue line. You see that blue line? That x equal to line, 1. Oh. That is x equal to y. And x equal to 1 minus y, this means it cos the axis at 1. When x equal to 1 minus y means when x equal to 0, y equal to 1. So x equal to 0, that is 0, y equal to 1, which is that point. And the slope is minus 1. So it is that line. Alright? And I do integration from x equal to y, that first line, to x equal to 1 minus y, which is the second line. Oh, second line. Then the outer integration limit is y equal to 0. Y equal to 0 is that line. Right? And then y equal to 0.5. Y equal to 0.5 is that line. So I do from left to right and bottom to top. Okay, left to right and then bottom to top. When I change the integration limit, I have to preserve the direction. Okay, there's no guarantee that if you flip the sign twice, you get the same. Like instead of left to right, bottom to top, you do right to left and top to bottom. You don't know if that function f will behave the same. Okay, you never know because I don't tell what is function f. Some function is okay, but not always. So we need to preserve the direction. Okay. Okay. Instead of left to right, bottom to top, this time I do bottom to top and left to right. Bottom to top means, oh, now it's a little bit difficult because bottom maybe one line, but top there are two functions. So this means I have to split into two functions, right? Not just one. So I do bottom to top like that first, the pink one, and do left to right, which is that to that. So I get the first part. Then I do bottom to top, that to that, and left to right, that to that. That's the black one. Right? So bottom to top, previously we do dy dx, now we will do, previously we do dx dy, now we will do dy dx. Dy dx means, okay, bottom to top, y equal to 0, y equal to x. So that's why I simply put 0 and x. See that? And then left to right, that line to that line. That line is x equal to 0, and that line is what? What is the cross point? 0.5? How do you know it's 0.5? Because that's where it crosses, right? X equal to y and y equal to minus 1. You can solve those equations. So the cross point is 0.5. So I integrate from x equal to 0 to x equal to 0.5. That's how I get that. Good? The second time, I do from 0 to 1 minus y. So that's how I get 0, or instead of 1 minus y, it has to be y equal to something. So I have 0 to y equal to 1 minus x. And then I still do left to right, which is that line to that line, 0.5 to 1. That's how I got that. Okay. This line, the cross point, y equal to x, right? I put, instead of y, I put x. I get 2x equal to 1, so x equal to 0.5. Not a problem. Question. So we have to preserve the shape of the domain. Maybe when we split, we have to break it into two integration, okay? Because we cannot cover in just one function. Ham, do you have question?
No.
Victor, question? No? Okay. Let's move on. Our last time was 15 minutes. But I think very easy for us. Just 5 minutes will be enough. Huh? Okay, but that's for later. Okay. That's optional homework due in December. When do you want? You want 1 day before the grade submission? Or you want 1 day before final exam?
For grades, initially for grades.
Not just that for.
So when you do the final exam, you don't know what your score is, right?
Yeah,
But you may have some feeling, okay, maybe I have to do this. Yeah, I will announce that accordingly in the blackboard. How about that? Is that help? You don't have to do any of this, okay? But last year they did it. Okay. Alright. Now let's talk about closure relationship. We used it already, but maybe we didn't talk about it much. Closure relationship, VTB equal to Z0 VM plus V drift. This is closure relationship to calculate VTB. A must. No model can just populate VTB. Maybe if you do open form, maybe you tell me what is VTB without closure relationship. So C0, 1.2 for turbulent, 2 for laminar, and Reynolds number use slug body Reynolds number. Okay? Slug body Reynolds number require the knowledge of slug body liquid hold up. See that? Slug body liquid hold up is from another closure relationship. Okay? Then V drift is that equation, okay, for any angle. If we plot it, we will see that V drift behave like that. So at 0, we have some drift velocity. And the explanation for that is when we are at 0 degree, we put some bubble in, bubble move, it deform. Raymond did the test, okay? Previously I had this question. Like, okay, some people find the drift velocity by trap gas pocket inside. Okay, open that valve. Okay, then liquid move here, and bubble expand, like elongated. Choice 2 is close this end, open that end, let water come out, gas going in, and bubble move inside. Which way is faster? Raymond told me it's the same, it's more or less the same. Okay. Alright? That's what he found. So it's more or less the same. That's how people measure drift velocity. Okay. I would suggest to open it. It's a little bit more mess if you open it. But okay, Raymond found that it's the same. But you may find something different if you do it with oil. You may find something different if fluid property change. I don't know. By definition, we do it at 0 mixture velocity. So translational velocity will be equal to drift velocity. Translational velocity is the velocity of the interface. VTLS, most of the time we don't need it. We need it when we do what? Taitel-Barnea model. Okay. And Taitel-Barnea suggests C0 for this equation, not previous equation, equal to 1 for angle equal to 0. Okay. This part is kind of bubble rise velocity, but we will cover it later. For vertical flow, 1.2 is the most probable value. Okay. That sigma is Newton per meter, or 0.072, or 0.07 SI unit. Okay. Newton per meter, not millinewton per meter, use Newton per meter. Everything has to be SI so that it's consistent with the original application. HRMS, we need to do this first. Did we use 0.7 or 0.6? I think it's 0.6, right? 0.7? 0.6? I don't remember, but okay.
It was 0.7 times 0.6.
0.7 times 0.5? Okay, so that's correct already. So we have several correlation. I suggest Gomez. Okay. Any of that will be fail for a case of high viscosity oil. For high viscosity oil is something else. But okay, for low viscosity fluid, low viscosity means 1 to 20, you may use this. 1 to 5, this is very accurate. Okay, but okay, if viscosity go up, this will give you some number better than a random guess, but it's not that correct. Frequency, do we need frequency? Yes, double Hubbard need frequency, and there's a correlation for frequency. Instead of frequency, we may use slug length, slash 1/2. Okay. If you use both at the same time, something has to be adjusted. Otherwise, you don't have mass balance. Okay. And there's a suggestion, okay, less than 2 inch, 30 diameter, more than 2 inch, use this equation. Large diameter pipe, airways is much longer than 30 pipe diameter. Slug can grow along pipe length by picking up fin in the front of the slug but shed less at the back. For vertical flow, the observed slug length is about 10 to 20 diameter. Okay? So vertical flow, slug becomes shorter. That's the observation. Slug length and frequency, which one is more accurate? Frequency, of course. Okay? It's easier to count how many slugs than try to take a picture, stop it, and measure from the picture. That is difficult because when something moves, it could be like a little bit blur. All right. Any questions so far?